Howdy hackers, and welcome to another episode of FairLight TV. This episode will be about C64 Fastloaders, predominantly for the C1541, and the reason for this was a post on a Facebook group, but we will get over to the details of that. So let's go over to the actual content. Damn! So, on the topic of C64 Fastloaders, the reason for doing this episode in the first place is that Andreas Walstrom, Morpheus, the guy behind C64.com, both the webpage and also the Facebook group with the same name, he posted this. Dave McMurtry, is that it? Yeah, well, Commodore History, the YouTube account Commodore History. He posted something around C64 Fastloaders, and he did this looking into standard stock kernel loading and also a PIX Fastload, also asking why nobody did anything for a PIX Fastloader. Well, I guess first of all, answering that question, I would say that a PIX Fastloader wasn't a thing in Europe at all, basically. I think in the US, more people got a disk drive already when they bought the computer, so they had an urgent need for a Fastloader very early. Whereas in Europe, we tended to have disk drives only later. It took a number of years before we saw the value of disk drives in comparison to the cost. And by then, a PIX Fastloader was already sort of obsoleted. So when we started buying disk drives, we needed a new cartridge, and that cartridge would be something else than a PIX Fastload because they were not competitive anymore. Whereas in the US, disk drives early, a PIX Fastload really early, and it was still sort of current when the Americans bought most of their disk drives. My theory, I'm not saying this is correct, but that's what I think. So, and Dave, he goes through this in a very gory details by connecting an oscilloscope to the serial bus and then showing the communication over the serial bus. And I'm sure, and I mean, there are multiple paths to the same goal. Educating people over how serial interfaces work and how speed loaders work. That's not really too appealing to me. I'd like to see it from the top and then going down. And so I think there is a sort of a risk that people will see this as missing the forest for all the trees. You get a lot of sort of oscilloscope details, but it wasn't too obvious how the overall principle work. But each to their own. I'm here pointing at Dave's video, so I do suggest that you watch that one as well, because I think it's super well made, and he's done a great job kind of explaining it. Even if it's not sort of my preferred approach to it, it's still very good. So great work, Dave. Keep doing that great work. And I understand from this that if you're going to kind of sound serious, you need to prove that you have an oscilloscope. So here you have an oscilloscope. That's probably the only thing you would see with an oscilloscope from me, but yeah, here it is. It's a nice picture of one. Okay, let's take a bit of a background here. The C64 is a computer. It has RAM, it has ROM, and it has a number of I/O registers, and it's connected to a screen, a full computer. Normally, in modern computers or other computers, you would have a drive mechanisms connected to the actual computer, and the actual computer would interface the drive mechanism. So the DOS, the disk operation system, would be in the same ROM as the rest of the system's stuff that you would need to have. So it wouldn't be very different. So this is the case for PC, this is the case for the Amiga, but it's not the case for the C64. On the C64, the disk drives are their own machines. So it's basically a really lame other computer. It's a computer that has its own CPU, it has its own RAM, and the only function it has is looking at what comes in via the serial bus and reacting to that. But the cool thing is that it has the drive mechanism. It is the host for the drive mechanism. So from a protection point of view, that meant that you can actually hide stuff in the RAM of the disk drive, because once the disk drive was handling that, it was no longer responding to serial commands, which means that you, if you had access to the computer, couldn't access what was in the disk drive. So if you look at previous episodes I've done, the core of the protection is the routine that is sent to the disk drive, and then every trace of that is scratched inside the computer, and then you had something in the disk drive and you can no longer access it because there was no like a machine code monitor that would be able to run inside the disk drive. There was no freezer cartridge that could access the content of the disk drive unless it was responding to normal commands from the computer. All right, and that of course had nothing to do with this picture, but that was sort of a precursor to what we have here. So loading, because we're talking about fast loading, but let's talk about the sort of the aspects of loading and how that works, and then we would look at how you could sort of optimize each of them. So first, the computer sends a command to the drive. I would like to load this. Drive then searches the directory, and directory track is track 18 or 12 if you're talking hexadecimal, sector 1. And then that sector contains 8 entries for directory entries. If the file name is amongst those 8, then the disk drive would only start jumping to the track and sector that is pointed out via the directory entries, and we will look at that in more detail. But if it isn't there, then it will look at the first 2 bytes on the sector, say that points to the next directory sector. So there is a chain of sectors where the 2 first bytes in those sectors point to the next one, until you reach the last one, which starts with a 0, indicating, okay, this is the last sector. There will be no additional sector. If the file hasn't been found when you reach this and looked at all the entries, the file is not on this disk, and then it will return an error saying that, well, I didn't find the file. But if it does find the file amongst one of those entries in the directory chain, it will look at the track and sector that is associated with that entry, and then it will start moving the head to that track and then looking for that sector, reading the first sector, the first 256 bytes. And as with the directory sectors, the first 2 bytes are pointers to the next sector. So either it's track and sector, or there is a 0 with the first byte indicating that this is the last sector of the file, and then it loads the number of bytes that are relevant for that sector, and then the file is loaded. But looking at it from sort of the logic perspective here, so we read the sector, and please mind that the data you see, the normal 256 bytes, it's not stored like that. I will get into the GCR encoding in a few slides here, but so the data is stored in GCR format, where 4 bits are converted to 5 with the sole purpose of ensuring that you don't have 3 zeros stored to the drive subsequently or in a sequence, because it can only safely handle 2 zeros in a row. I'm not going to go into the details before we get to the GCR slide in a few slides, so bear with me. So 256 bytes loaded, but in GCR format, so it's actually 320 or whatever it is. They are then 2 bytes that are the link bytes, and then 254 bytes of data. 254 bytes of data sent to the computer over the serial bus, and if this was not the last sector, it will go back to item number 4, get to that sector, load that in, do a GCR decoding into normal bytes, and then it will send them over the serial bus until the file is sent. This is the normal flow for loading a file using stock kernel. Right, let's go into sort of the structure on the files here. So this is a logical representation. I've taken this from Project Area 51. And I've just fed a disk image into my favorite tool. What's it called? DearMaster? Yes, DearMaster, right? DearMaster 3.1 or 3.15, I think it is. There are a few nasty bugs in the updated version, so I'm still sort of keeping the old, even if it also lacks a number of features. Well, we're not here to talk about DearMaster here. We're going through the directory here. So here you would see my disk. So it has Dalek intro, it has Dalek attack, the main file, and then a number of dummy files just to kind of proper up the appearance of the directory. They have absolutely no relevance. And then you have the whose levels, so that is an IFFL file. And if you remember this game, it has been featured before. It has been featured in the episode where I go through my own favorite cracks. Because this one is an IFFL, it plays the game's own music while it's loading the levels. So yeah, I think that one was really nice. And so this is how it looks when you do a directory dump. But if you look at the actual sector data of that sector, that looks like this when you do a sector dump or a directory dump, it will be something like this. So first you have the 2 bytes that should point to the next sector in a directory chain. You would have them here as this. The next one is the file type. So 82 means, and for helping us, we would have this table, and you can also see it here. The lowest 3 bits, so bits 0, 1, and 2, indicate which file format it is. And you can have rel, user, program, sequential, or deleted. And then you have bit 7, which marks if the file is closed or not. So if bit 7 isn't set, you would have one of those asterisk. I think it's called a splat file when it's not properly closed. And you can also set bit 6, and then you have this little bracket saying that this one is sort of write disabled, so it locked. You cannot just delete it. You need to unlock it before you can normally scratch it normally. All right, so 82 here means that you would have the last 3 bits would be set to 2, and that is a PRG file. So you see the value of this is 1, the value of this is 2, and the value of this is 4. So a PRG would be 2. And the value of 7 is 80, or hex 80, so 128. So, and that's what you have here, 82. So 80 being this and 2 being that. A fully properly closed program file. That's that. And then you have 11.0. That's the location for the first sector of the file. So when the DOS looks for Dalek intro, it will look at this entry here. It will find that, okay, yeah, this is the file I'm looking for. Where is it? It is on 11.0. So track 17 sector 0, if you want to express this in decimal. And then you have the actual file name. It's this 44, 41, 4C, blah, 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 until 54 here, which you can also see here. If I would have had a shorter file name, you can see here that I filled all the potential entries of a file name, but if my file name would have been like 1 character shorter, it would have padded that remaining one with A0. So you need to pad the ones you're not using with A0. And then you have a number of entries here, 00000, and they are not used for anything. They are, I guess they're used for relative files, and nobody uses relative files. I think Yeos might use it, but it's very rare that you actually use them. So don't worry about those for normal purposes. And then at the very end, you have 38 and 00. And these are, so that's sort of the length of the file name. The length of the file name. Oh, file size in sectors. So 3800, it's the low byte and high byte, and 38 is 56. So 38 hexadecimal is 56 in decimal. This is only a cosmetic one. So if you change this, the directory would reflect your change. So you can have like 1000 blocks here. That will work absolutely fine. It will your directory would show 1000 blocks, but when you load it, it's still the same 56 blocks that are going to be loaded. So if you validate the disk, you can have it reset this, or if you have a special tool for it, you can check if this is correct, if you compare it to the actual number of tracks and sectors that is in the file. But normally you are totally free to change this at will, and the computer will never bother about it, because the only thing it's used for is presenting the directory. Yeah, so I think this was sort of how the C64 directory entries look. Yeah, if you have any questions, do post them in the comments down below, and I will try to answer them as good as I can. Okay, and then you have the complexity. So you have data, the 256 bytes, and you tend to think that that is sort of what's stored on the disk, but it's not. It's encoded. So it takes that data and stores it on the disk. So the actual track and sector has a binary or a header and a tailer on the sector, and then the actual sector is stored here in GCR format. And again, the reason is that the 1541 cannot handle too many zeros in a row. It can basically only handle 2 zeros in a row. So it encodes this 4-bit sequence with a 5-bit sequence, where the 5-bit sequences are picked so that none of them contain 3 zeros in a row. That's the only target of this. Remove the occurrences of multiple zeros in a row. I've taken this table from LFT's article on real-time GCR encoding, or should be GCR decoding, I guess. There will be a link in the description to LFT's article. It's absolutely amazing, but make sure you understand a lot of drive coding before you read it, because it's sort of the next level. You will not be able to digest it unless you're sort of well acquainted with a number of aspects of the disk drive. Even if LFT is explaining it better than anybody else, you still need some sort of basic understanding before you get there. Otherwise, you would still be clueless after watching it. All right. Just a short commercial break. We're not making any sort of money on this YouTube channels, and we don't have Patreons that pay in stuff. Yeah, that's sort of not what we are doing. So if you would like to support us, please subscribe and share, because they are the two things that you can actually do for us. Subscribe means that you are watching the next video. Sharing means that you are providing the word of mouth spreading of our stuff and reaching people who might be interested who we haven't been able to reach via our normal channel. So could you do me the favor of sharing this? And what you can also do is buy a t-shirt on redbubble.com to prove to your friends that you're actually watching this. It's also something we would strongly appreciate. There will be a link in the description for that as well. So, and I won't bore you with this anymore. So let's go over to GCR encoding. No, that's that was not because I wanted to show that picture again. We are talking about now going to talk about how we should optimize the different steps to get to the fast loader. How can we get data from the disk drive into the computer faster than it's currently doing it? Serial data. Let's just look at serial data. What happens? So you are sending serial data on the bus, but it's really, really slow. What you can do is having a little routine inside the computer and having a little routine inside the disk drive and taking over the serial bus, sending it in a more efficient manner. Because the normal operation of the serial bus is that you are anticipating that there will be, or there could potentially be a number of other devices connected to the same daisy chain. So there might be a printer or a second disk drive. So you cannot use all the pins that are actually there, because if you start communicating like that, one of the other devices might think, oh, well, this is communication for me. And then it could start talking. And of course, if one of the other devices starts talking while you are trying to do a time critical loading, of course that will fail, because that will be somebody like speaking who's not the guy that you are listening to, and of course that would sort of interfere the presentation of the first guy. So, but what you do there then is, anyway, you are sending a memory write, that should be a memory write and then a memory execute. Memory write is the command you send to the disk drive. Hey, I'm interested in writing this little sequence of data into the memory of the computer, of the disk drive. And oh, by the way, can you execute that as well? So that is what memory write and memory execute is doing. And you need to do that because you need to be both on the sender side and on the receiver side of this communication. Because if you're only sitting in one side, it doesn't really matter if you know how to make it faster if the other side doesn't know that, because then you wouldn't have the faster communication. So how do you do to actually speed this up? Yeah, well, first, what you are actually doing is that you are skipping a lot of the handshaking, and you are taking advantage of the fact that the disk drive is running on exactly 1 megahertz and the computer is running on roughly 1 megahertz. So if you're just sending small bursts like a byte, you really don't need to handshake between every bit. If both the sender and the receiver are aware of the sort of number of cycles it takes before each new bit is set, then the correct bit is there when it's ready to be received. So that is sort of the predominant way of doing it. No handshaking, or remove all or as much as possible of the overhead of the current handshake, which is really needed for the serial bus where there might be multiple instances or multiple devices connected. All right, so a number of issues here that you need to consider if you want to implement the fast loader. First of all, as I said, the computer, if it's a PAL machine, it runs slightly lower than 1 megahertz. And if it's an NTSC machine, it runs slightly faster than 1 megahertz. And unless you are making corrections based on PAL and NTSC, there is a degree of risk that your loader will only work on one of the systems. Sorry. And to be honest, this is also one of the reasons why a number of games do not work. If you buy an original from the US and you try to run it on a European machine, or vice versa, it could very well be that it was sold on one market and it had a loader that was only sort of compatible with that TV system. And if you try to load it on the other TV system, it wouldn't work. Even if the game itself would work and would need no sort of modifications to run on the other TV system, the loader itself could be a hindrance for having it work in the other TV domain. Do you want to support only one or both? If you want to support both, you have to make sure that you are actually sort of making that time adjustment. 2-bit transfer. There is only one data bit. I'm sorry for being cold. There is only one data bit, and there is a clock bit, and then you have the attention bit. If you would like to have a transfer that uses more than the data bit, and you are going to allow other devices connected to the daisy chain, that is going to be complex. So either go for 1-bit transfer or go for the option of sort of only allowing one entry on, or one device on the serial bus. And a really tricky aspect as well is if you're going to run with the screen off, that means that no VIC interference would happen. Whereas if you run with the computer screen on, you're inviting a number of potential side effects, because the VIC interferes and the CPU just sits back and does nothing. So on every bad line, which is the first pixel line when the computer fetches, or the VIC fetches the data for the characters. So every 7th line will be one of those where VIC steps in and steals 40 cycles. And if you are in one of those time critical phases where you are going to send data and receive data with no handshake in between, yeah, of course that will fail if that happens when the VIC sort of suddenly takes precedence and the CPU and the computer just sits there doing nothing, whereas it's bombarded by the disk drive by new bits that it's not going to receive. It's just sort of, oh, I didn't see that because I wasn't here. So you need to ensure that your loader is not operational on the bad line. You need to ensure that you are on the other lines here. So avoiding triggering a new byte from the disk drive on a bad line, because if you're allowing it on the bad line, it will fail. The same with sprites. Sprites are very difficult to control in this aspect. So there is basically only the option of turning sprites off. So 0 in DO15 and you're good. There are no sprites, because sprites take 2 cycles or 3 cycles and a few cycles. And if there are more than one on the row, it doesn't take... Yeah, calculating the number of cycles that are stolen from every raster line, it's very difficult if you have sprites there. So just turn them off. If you want the screen on, that's fine. Just don't have sprites there. An IRQ loader, normally you should basically not have any IRQ, because that's also one of the aspects where the CPU is diverted from doing what it's doing and servicing the interrupt instead. And if that happens in the little instance when the computer is receiving bits from the disk drive, then of course it will fail. So, but there are IRQ loaders. So what they do is that they have a set interrupt in the beginning of that little time critical transfer, and then you have a CLI, clear interrupt flag, at the end of that transfer. So then you can have your little routine that sends the bits, and then you can service interrupts at will. And there is no problem with servicing interrupts beyond that. And IRQ loaders, you can read a lot about IRQ loaders. To be honest, I think most of them originates from the original game G.I. Joe. Basically, everybody I'm aware of stole the core of their drive routines from the game G.I. Joe. All right. All right. So what can be optimized? Sending the routine to the disk drive to ensure that you had both the sender and the receiver. Of course, that takes a bit of time. And if you're loading a very short file, it might take longer to send this fast load routine and then load a very small file. But you don't know when you're loading a file if it's a short one or a long one. So the key to this would be to implement fast load routines in the ROMs, both on the computer side and on the disk drive side, because then you would only need to say, hey, I want to fast load. And then the disk drive would turn into fast load mode and you would be good. Then that would be loading fast via the built-in routines for sending and receiving. Track reading. So when the computer reads a track, it doesn't read a full track. There is not enough memory to read a full track. So it reads a sector, again in GCR format, which is then converted into like the normal bytes, and then it needs to find the sector. And yeah, depending on where it is when loading, you could have the situation where it needs to do basically a full lap before it finds the sector it's looking for. So there are a number of disk systems where you would load the entire track at once into a RAM buffer. So when the computer or when the disk drive is looking for the next sector, that is already in the RAM in the buffer. So you don't need to read it again. You just read it from the RAM, which is of course massively much faster than finding it and decoding it from disk. So originally, the game has the disk drive has only 2 kilobytes of data. It's from 0 to 07 FF, but so you need something which is sort of a RAM expansion in the drive for this to work. Okay, and we've discussed the communication over the serial bus and how you could fiddle to get the serial communication faster. But of course, the other path here is not to fiddle with the bits inside the serial, but having another parallel connector, a parallel connection between the CIA, one of the 6526s, inside the C64. So you connect that to the user port. And then you have one of the VIs, the 6522s, inside the disk drive. And you have cables, or a cable with like 8 bits that connects them. And then you can still use your normal handshaking and communication over the serial bus. But then when the drive is going to send stuff, like send a full byte, it will send a full byte over the parallel port. And then the full byte is fetched on the C64 side without any shifting or decoding or anything. Here goes 1 byte, 1 go in 1 handshake. Check. All right, let's go into the types of loaders here. Okay, types of loaders. The plain vanilla old stuff is things like Pink Floyd, not the group, but the loader. It was a specific little file you loaded, and then once you executed that populated the disk drive with a fast loader, and then you can load the subsequent file a lot faster. So if you had a file that you wanted to load, but it was rather big, if it was big enough, there was a benefit loading this and then use that to load the bigger file. But of course, there is a trade-off here, and it's very, very inconvenient. But think of this like the tape loaders, and pretty much using that to kind of kickstart a bigger file, and the total time would still be less. I know a number of people who used Pink Floyd. They reversed engineered and implemented into their own project. So if you had something that loaded several files, it would use Pink Floyd internally in their productions. And the FairLight demos from the 90s used actually Pink Floyd for loading the next part. All right. But again, you load a file that uploads this fast loader thing into the disk drive, and then there is communication for loading the next file. So there is still the upload part to the disk drive, and also the loading part of the actual fast loading software here. Cartridges made it in as sort of the big thing. Everybody needed to have sort of a utility cartridge, because there were so many additional features that were so handy to have, really accessible, and the cartridge was the logical vehicle for that. And of course, fast loader is the foremost feature you want from a cartridge. And again, that's why Epic's fast load was such a success in the US, because everybody realized that they wanted a fast loader, and Epic's was such a fast loader. So it's basically the same thing as a Pink Floyd, but it's based in ROM. So it still does the same thing. It uploads a little routine into the disk drive, and then it can take advantage of owning the communication over the serial channel. The other approach is implementing the fast load routine inside the ROM. But then you of course need to have it both in the ROM in the disk drive and the ROM in the computer. So GFIDOS was one of those. First of all, the kernel in the computer and the kernel in the disk drive, they are both jam-packed. So it's not like you can squeeze in a fast loader there without sacrificing anything else. You need to have something go. And one of the first things that would be sort of relevant to kill would be tape routines. So if you look at GFIDOS, there are no tape routines in GFIDOS, because all that memory is taken by the fast load code for GFIDOS. GFIDOS is a super compatible, really fast and efficient loader. It's compatible with nearly anything. And you also had this little switch normally on if you bought it properly via CMD. So you could turn it off. But again, if you wanted to play tape games, yes, then you needed the switch to ensure that you turned GFIDOS off, because you needed to have standard kernel if you wanted to do tape loading. The other part was taking fast loading to another level, and that was parallel loaders. You had like vanilla loaders, and Speedos is sort of the one I'd like to point out here. They were only changes of ROM in the computer and changes of ROM in the disk drive, and then the parallel cable. And of course, they were a lot faster than most of the serial ones. It has one of those key drawbacks. It can only connect basically one drive. It's in theory it's possible, but I've not seen any really working instance of somebody having multiple disk drives connected using a parallel system. Whereas if you go back to GFIDOS takes over the serial bus, but it can fast load. If you have 10 or 4 disk drives, they can all load using GFIDOS, and it works fine. So GFIDOS works really well for us, who back then, first of all, didn't really... we needed to have our 1581s because we needed to store more data conveniently than would fit on a 1541. And of course we wanted our fast loader. So GFIDOS was basically the only option if you had more than one disk drive, because then all the parallel options were out of the question. So a fast serial one that sits in the kernel of the computer and also the ROMs in the respective disk drives, yes, go for Jiffy DOS. That is the best option for that scenario. But during most of my first years, I was using something called Professional DOS or Disk Demon. I basically had... I don't know which one I had, because they were the same. They were sort of the same technical solution sold under different names in different markets. So you had Dolphin DOS, Project DOS, Turbo Trans, Professional DOS / Disk Demon / Rapid DOS, basically being 3 different instances of the same thing. They featured a ROM in the computer, again with an on-off switch, and of course a parallel cable, and then they had more ROM, so it expanded the ROM that sits in the disk drive, and it also adds RAM into the disk drive to buffer full tracks, I guess, was the purpose of that. What you see here on the picture is, I think that one is a Professional DOS or a Disk Demon, and you see the serial cable that sits there. And you see here that, oops. So here is a little daughter board that extends, I don't know if you can see my mouse pointer, but from the parallel cable you will see this extender here, right? But I should also mention a number of sort of the systems that us hackers use. So we typically implement fast loaders if we have something that loads, if we do a game that loads subsequent data, that means that we need to install a fast loader, or most of the time that means that we install a fast loader. And we tend to have one which is a combination of a real-time depacker and a fast loader. So you get a byte from the disk drive and then you feed that to the decrunch routine. The beauty of this is you don't need to have any depack buffer. You might have a little buffer of 256 bytes, but you don't need to load the entire file into one place in memory and then depack it to another place in memory. That will be a total waste of space, and normally when you retrofit a game, you don't have that kind of a space. You would be lucky if you find the 2 pages where you can stuff your fast loader and real-time depacker. A variant of this real-time depacker is IFFL, and I had a special episode on IFFL. So so it's a file linking system where you take files and you chain them into a bigger file, as we saw with the Dalek's attack in my description of the directory. And the beauty of that is that, first of all, it saves the little thing, the little spare in the end of each file. So if you have 10 files, the last sector is always allocated, but it might only be filled until half of it. Statistically, it's filled half. If you have 10 files, if you join them, the total combination of that joint file should be 5 blocks shorter than if you add the individual files, statistically. And that tends to be true for most of the cases. But what you need to do is, when you launch the IFFL, when you launch a scanner, because this file could be if you do a file copy, you don't know where on the disk it sits. So if you are going to segment number 4, you need to have a track and a sector and an offset of that position. The offset is a given because that is sort of already known when you generate the IFFL file. But track and sector could be totally different from the first disk it sits on compared to any other disk it was copied to. So you are launching a scanner that scans the track and sector for each of the segments of the files. But once you have that is a faster directory. If you say that you would like to load segment number 4, you just look in your table and you directly knows the track and the sector of that 4th segment. Compare that to looking at the entire directory, spanning the different sectors of the directory. That takes so much longer than what an IFFL would do for you. So if you have multiple files, then IFFL is for sure something that would save space, but it would also save loading time because of removing the necessity for scanning the directory track. On the other hand, IFFLs, they can only handle so many files. They can basically handle up until 127 files. I haven't seen anyone that's reliably supports really much more than that. So yeah, they might have a use case where they are beneficial. For me, they are mainly a hassle. But yeah, well, anyway, that's IFFL. If you want to know any more details, I think it's like episode 3. Demo load systems or demo system loaders. So they are also this combination of Fastloader and Depacker. Since this is not retrofitting, these systems can sort of impose more requirements on the user, but they can also return more features for you. So again, data is stored directly on the disk. There is no relevant file name. The loading system handles the tracking sector where everything is. And typically there is some sort of scripting where you say, I would like to load this now, and then the loading system knows where that is stored on disk. And the directory is basically a dummy thing. It's there for show, but you don't really need it for anything. And also that means that you can actually store more on the disk, because you can make your demo system use the entire track 18 as well. Well, except for the first 18.0 and 18.1, you would need to have them allocated for disk DOS purposes. But the rest of the track 18 you can use for storage of demo data as well. So I've taken Spindle here by LFT as the example. You have Bitfire by Bitbreaker, and you have Krill's loader also, which I think sort of fits here. Since I'm not really a demo coder, these are the 3 options I could point at, but I'm sure there are others that are absolutely brilliant as well. I'm not really sure if more than these are sort of known to the general community. It might be that certain groups use their own stuff for this, but don't spread them. I wouldn't know. These are the ones I know of. Spindle is absolutely amazing. When you reading up on it, you do a bit of a scripting thing, and then you do your demo, and you let Spindle handle all the mess with multi-disk, all the linking, all the storage on disk. It generates a number of D64s, and you're done. It takes care of a lot of the complexity around loading and depacking and all of that. So these are cool, but the requirements on those, if you compare that to the requirements of a loader for cracks, where we must have file name based loading, we cannot have direct track and sector, because then it wouldn't be counted as a proper crack. That was everything for today. Thank you for joining me watching on how to do speed loaders on the principle level. Again, if you are into oscilloscopes and would like to understand how loading works on a electronics level that you can only watch using an oscilloscope, then I suggest using Dave's video instead of mine. Thank you for watching. Bye bye.
This station is now the ultimate power in the universe. FairLight.